A traffic jam that appears on an empty-looking motorway, for no reason at all. A wall of water racing down a valley after a dam fails. The crack of a sonic boom. Three phenomena from three different worlds: cars, water, air. They are the same equation. Not similar. The same. One line of mathematics predicts all three, and it predicts the strangest thing they share, that a smooth, gentle beginning can, in a finite and calculable time, turn into a sharp wall, a discontinuity, out of nowhere. This is the scalar conservation law. By the end of this video you'll look at that jam, that flood, that boom, and see the same crossing characteristics underneath all three. No black box, everything you see is a real numerical solution, computed, not drawn. Start with the most basic bookkeeping in physics. Pick any quantity that can't be created or destroyed, only moved: mass, cars, water. Draw a little box. Whatever is inside can only change if more flows in one side than leaves the other. Write that down and shrink the box, and you get the conservation law exactly. The rate of change of the density U, plus the spatial change of its flux F, equals 0. That's the whole skeleton. Everything interesting, everything, lives in one choice: how does the flux F depend on the amount U? Pick a flux, and you've picked a universe. Take the simplest nonlinear choice there is: let the flux be U squared over 2. This is the Inviscid-Burgers equation, and its meaning is the key to the whole video. The speed at which a value travels is U itself. Big values move fast. Small values move slow. Hold that thought. It's the engine of everything that follows. Here is a smooth wave, a simple sine, evolving under that rule. Watch the top. Because tall parts move faster than short parts, the crest chases down the leading edge. The back steepens. The front leans forward, like a wave approaching a beach. Underneath, the reason is simple. Every point carries its value along a straight line at its own speed. These are the characteristics. Where the fast lines catch the slow ones, they cross. And at the instant they first cross, the wave would have to be vertical, then in two places at once. Physically impossible. And you can predict the exact moment. The braking time is -1 over the steepest initial downslope. For this sine, that's exactly t equals 1. Not roughly. Exactly. Run the solver, and at t equals 1 the slope goes vertical, right on schedule. Nature's resolution to the impossible wave is to insert a jump, a shock, a moving cliff in the solution. And its speed isn't arbitrary. The Rankine-Hugoniot condition sets it at the difference in flux over the difference in value across the jump. For a drop from 1 to 0, that's 1/2, and that's exactly where the computed shock goes. Change what you means. Let it be the density of cars, ρ. The flux is now the traffic flow. Empty road, no flow. Bumper to bumper, also no flow, nobody's moving. Maximum flow sits in the middle, at half the jam density. This is the LWR model, the same conservation law with a new flux. Here's the everyday mystery. Free-flowing traffic runs into a denser patch ahead. The same steepening happens, free flow piles into slow flow, and a shock forms, a sharp boundary between moving and stopped cars. That boundary is the back of a traffic jam. And here's the payoff: the math hands you free. The shock speed comes out negative. The jam's back edge travels backward, upstream, against the traffic, at about 20 kilometers per hour, even though every car is moving forward. You felt this: you brake for a jam with no cause, and minutes later it's gone from your mirror. You didn't drive through an event. You drove through a shock wave. And the reverse? A light turns green. The dense jam doesn't jump to empty, it fans out smoothly, front cars leaving first. That smooth spreading is a rarefaction, the exact opposite of a shock, and the other thing the equation can do. One more change of meaning. Let U be the depth of water, the flux from shallow water theory. Hold back a reservoir behind a dam, 4 meters deep, dry ground below. Remove the wall. This is the Ritter solution, exact, from 1892. It has both faces at once. Upstream, the surface fans out smoothly into the reservoir, a rarefaction, just like the green light. Downstream, the leading edge is a sharp wall of water over the dry bed, a shock front, just like the traffic jam and the braking wave. The equation tells you exactly how fast that wall moves, twice the square root of g times the original depth. For 4 meters, about 12.5 meters per second, 45 kilometers an hour of water, with no warning. And a strange exact detail, the depth right at the old dam line stays frozen forever at 4/9 of the original, 1.78 meters, no matter how long you wait. This is why the same equations describe dam breaks, flash floods, tidal bores that surfers ride upriver, and the run-up of a tsunami. All the same moving wall, all the same conservation law. So step back and see it whole. One equation, a conserved quantity, plus the gradient of its flux, equals 0. Change only what U means and what the flux is. Velocity, and you get gas dynamics and the sonic boom. Car density, and you get the phantom traffic jam crawling backward up the motorway. Water depth, and you get the flood front. 3 different worlds, 1 skeleton. And the deep reason they rhyme is always the same picture. Whenever the flux makes fast states pile up behind slow ones, characteristics cross, the smooth solution tries to become multivalued, and nature resolves the impossibility with a shock, a discontinuity whose speed is fixed exactly by conservation alone. That's the quiet power of a conservation law. You don't need to know what's inside the box, cars, water, air. Only that the stuff is conserved and how its flux depends on its amount. The shocks, the jams, the floods, the booms all follow from those 2 facts. One line of mathematics, wearing every costume nature hands it. Derive everything. Trust nothing you can't derive. See you in the next one.